next unit that we're going to study is basic probability. So far, we've been looking at descriptive statistics, which has to do with how we organize, summarize, and display data. Now we're going to go to the inferential side, which involves using a sample to draw conclusions about a population. And probability is the major tool for this. So first, there's going to be a lot of vocabulary in this section because this is the introduction. So here are the first four terms you need to know. A probability experiment is just an action or trial through which specific results, counts, measurements, or responses are obtained. So I gave you an example of rolling a six-sided die. An outcome is what we call the result of a single trial. So, for example, if we were rolling a six-sided die, an outcome might be just rolling a 2. And very often you'll see that put in set brackets to represent the set of outcomes. The sample space is the set of all of the possible outcomes. So for rolling a six-sided die, inside my set brackets, I would put all the possibilities. I can get a 1, 2, 3, 4, 5, and 6. And then an event is a subset of the sample space. It's one or more possible outcomes, and it's the specific thing that you're looking to happen. So, for example, an event could be rolling a 5. So let's look at a first example here to see some of the tools that we use. Survey consists of asking people for their blood types. There are 4, O, A, B, and AB, including whether they are Rh positive or Rh negative. Determine the number of outcomes and identify the sample space using a tree diagram. Now, a tree diagram is a great organizational tool because one way to go about doing this is to just list all the possibilities. So you could try and make a list of, okay, I could be blood type O, which is Rh positive, so O positive. I could be blood type O, but negative, and so forth. And when you're dealing with a small set of information, that's not too difficult to do. But if you start having more options, if there were 20 different blood types, very often you can miss one when you try just to create a list. So a tree diagram is a way to organize the possibilities. It's called a tree diagram because it usually looks like a tree. And what you do is you look at the first set of information you're given, the blood types. There are 4. So you're going to draw 4 branches that all start from a central point. And you're going to label each branch with one of the possible outcomes, O, A, B, and AB. Then off of each of these, we're going to branch for the next option that we're looking for, which is Rh positive or Rh negative. So since there are 2 options at this point, you can either be positive or negative. We put 2 branches off of O. The same thing is true for A. There's 2 possibilities. For blood type B, there's 2 possibilities. And same for AB. So this is a completed tree diagram. And the way that you read the tree diagram to determine the number of outcomes in the sample space is by walking along the branches. So imagine starting here and choosing one path and choosing a path off of that. So you walk from the starting point to an end branch. This represents being O positive as a possible outcome. Then you walk along another branch and make a different choice. So I might start on the same path, but instead of taking the positive route, I would take the negative route to generate my next possibility. And you continue this process until you have followed every possible path from the start to an end branch. So I finished that process and generated all the possible outcomes. How many are there? Well, I just count 1, 2, 3, 4, 5, 6, 7, 8. I can also just get the same thing by counting the number of end branches on my tree. So there are, in fact, 8 outcomes. And when you're asked to identify the sample space, you are just listing all of these possible outcomes. And again, we usually do that inside of set brackets. Let's look at another example here. Suppose in my closet I have 2 t-shirts, one Sabres, one Bills, and I've got 3 pairs of shorts. And maybe this is, the only clean laundry I have. If I want to wear one of these shirts and one of these pairs of shorts, how many possible outfits can I create? So again, this is a situation where we could just try to make a list of, oh, I could wear my saber shirt and my black shorts. Or we can use a tree diagram to organize all the possibilities and make sure we don't miss any. So in this case, I would choose my shirt first, and there are only 2 options. Either I'm going to choose to wear the Bill shirt, or I'm going to choose to wear my Sabres shirt. And then once I've decided on the shirt, the number of options I have for shorts is 3. So I'm going to put 3 branches and I'm going to represent the 3 colors. So I've got my olive, khaki, and black. So here's my completed tree diagram. I can see how many possible outfits there are by counting the number of end branches. 1, 2, 3, 4, 5, 6. So there are 6 possible outfits. And if I wanted to list the sample space, I could in fact do that and list, okay, I could wear Bills with olive shorts, Bills with khaki, Bills with black, etc. Now, if you are observant, there's a way to predict this number of possible outfits without having to do the tree diagram. Notice the options for number of shirts and notice the option for number of shorts. So, how are the numbers 2 and 3 related to 6? If you multiply those together, that does predict how many different outfits I can make from 2 choices of shirts and 3 choices of shorts. So suppose I expand my wardrobe and I have 5 shirts, 6 pairs of shorts, and I decide to wear one of my 3 pairs of sneakers. The tree diagram is going to start to get crowded because I would have to start with 5 branches for the shirts. And then off of each of those, I have to do 6 branches for my shorts. And then off of each of those, I have to do 3 branches for my sneakers. So you can see that that would get to be a little bit crazy. But using the observation we just made, if I have 5 choices for shirts, 6 choices for shorts, and 3 choices for sneakers, I can just multiply those together, and I know that there's going to be 90 possible outfits. This is why it can take so long to get dressed in the morning because there's a lot of choices. So, this idea of multiplying the different options you have together to get the total number of possibilities is known as the fundamental counting principle. And all that says is the number of ways in which a series of things can occur is found by multiplying together the number of ways in which each individual thing can occur. In example 3, suppose you're buying a new car. We've got different manufacturer sizes and colors that you happen to like listed in the table below. In how many different ways can you select one manufacturer, one car size, and one color? Well, it's as simple as looking at how many choices you have for manufacturer, how many choices you have for size, and how many choices you have for colors. Multiply those together. 3 times 2 times 4 is 24. different ways. Now, very often we don't really care about listing all those possibilities. We want to focus on one in particular and know what the probability associated with that would be. But let's look at another counting principle example. Suppose the access code for a car security system consists of 4 digits. Each digit can be any number from 0 through 9. How many access codes are possible when each digit can be used only once and not repeated? The first important piece of information is that the access code has to be 4 digits. So I'm just going to put down 4 blanks, and each one of these blanks represents one of the digits in the code. So how many access codes are possible when each digit can be used only once and not repeated? So think about that. For the first digit, it could be 0, it could be 1, it could be 2, could be 3, 4, 5, 6, 7, 8, and 9. So there are 10 different choices of digits for the first spot. And again, keep in mind 0 through 9 represents 10 different digits. Now, if each digit can only be used once I make that first choice, I can't choose from all 10 digits for my second one. Why? Well, take a look at my list of digits. And if I decide my access code is going to start with a 3, and I can't use that again, now I'm down to 9 possible digits for the next digit in my code. And then if I can't repeat what I chose for my second spot, maybe I went with 7, well, now I'm down to 8 choices for the third digit and 7 for the last. Counting principle says we're going to multiply those together to come up with our answer, and that turns out to be 5,040. So that's a lot of access codes. Do I have more possibilities or less if each digit can be repeated? Well, if each digit could be repeated, then on each blank here, I need to list how many choices I have for each digit. I have 10 choices in the first spot. And in this situation, if I do choose 3 for my first digit, I can choose 3 again. So all the digits stay in play. Therefore, I'm going to multiply 10 times 10 times 10 times 10, or please realize that you can use exponential notation here. That's the same as 10 to the 4th power. And if you type that into a calculator, that's going to be 10,000. So I have many more choices if I allow repetition. Now, in the last situation, I'm given one additional condition. Each digit can be repeated, and I apparently repeated be repeated, but the first digit cannot be 0 or 1. So I'm going to put out my blanks for each digit and think about how many choices I have now. If the first digit can't be 0 or 1, then I'm left with 8 possible choices for the first spot. Now, after that, it says the digits can be repeated. So whichever of these digits I chose for my first spot, not only can I use that for my second spot, but I also now don't have that restriction about can't be 0 or 1. That only applied to the first digit. So in this situation, I would have 10 choices for my second digit, 10 choices for my third, 10 choices for my fourth. Multiply those together and you get 8,000. So the technique of the fundamental counting principle lets you just list your number of choices at each stage and then find the total number of outcomes by multiplying those together.